Hello.
Oh, we got there.
It's Roger again.
It's Roger.
You are the weakest link. Goodbye.
This meeting is being recorded.
Recorded.
Proper job.
Oh,
That's what you want, isn't it?
absolutely.
For those who missed it, we can pop a link to see it later. Hello, everybody. How you doing?
Oh, fine.
Evening.
Hi.
Evening, lads.
Evening.
Ladies.
He's off.
I heard John's voice there.
Yeah, just putting it through. I lost the connection. My little mouse is playing up. I probably need new batteries.
Might need Star 9.
Might survive better if you feed them.
Evening all.
Evening.
Evening.
Hello.
Dave,
Hello.
can I have your permission to feature your website or link to your website from our new website?
Yeah, no problem. Yeah.
Okay, this is what I've written. Dave Eagle's Virtual Astronomy Club. Not actually a local club, because you're in the section on local clubs. Not actually a local club, but certainly an accessible one. Follow this link to find out more. The VAC usually hosts 2 online lectures a week. A week? A month.
Hey.
Whoa.
Yeah.
I missed a few.
I wanted to have a word with you.
Catch up, Dave. Catch up.
Hang on, yeah, month.
There's never a dull moment, is there?
No.
Okay, that's thank you for that.
You ought to see us on the Astra Radio. Hey, Kat.
It's chaos, wasn't it? Oh gosh, yeah.
Yeah, couldn't make it last.
You on the radio?
Couldn't make it last night, Kath.
Oh,
You
yeah.
missed the classic.
Oh, you did. It was, yeah. What was it? Strawberry whip and bacon frazzles. Oh my god.
All right.
I heard that bit.
Yeah.
And I missed that for an AGM.
Honestly, yeah. Well, that's Mark Thompson's food suggestion for us all. So we're all a bit, we'll see.
Nice idea to go up and support him, wouldn't it?
Yeah.
Has anybody got details of that? Because it'd be good to raise that.
It starts. I think he starts it on the 12th. Is it the 12th of September? It
The
starts
11th. The 11th.
11th. Was it 11th?
Yeah.
Yeah. You could give a link.
Doesn't really matter. He's doing it for 5 days. You better catch it sometimes.
So it'd be good to mention that to try and get him some support.
Yes. Yeah.
And it's all for Bernardo's, isn't it?
Yeah. No. Yeah.
Excellent. Right, what's the time doing? Oh, it's 7 o'clock. There you go. We may as well crack on. Welcome everybody. Hope you're doing okay. Everybody managed to get a haircut yet?
No.
Yeah.
Mine's tomorrow.
We're not going to mention the whatever they call that game. But what about yesterday with?
Oh, that was awesome.
Oh, that was brilliant, wasn't it?
Fantastic.
Yeah.
Absolutely amazing.
Yeah.
Yeah.
My severe haircut is tomorrow.
Excellent.
I got mine in May.
I've got my second haircut booked for May.
Like a second vaccine.
Is that a Pfizer haircut?
Hi, Daz.
Hi, everyone. How are you?
Hello, you right?
Lovely, thank you.
Good, Dad.
Yeah.
Good. Right, welcome along, everybody, and good to see you all virtually. I can virtually see you, but yeah, okay. So I'll just go through my usual spiel before we let Julian loose.
Ooh, is that wise?
Not wise.
Only if he's got cake.
I've had cake.
Got cake. Yeah, so just going through my usual spiel. The Paddler is filling up with some really nice images people are taking, so just see those. Donations, we've got a reasonably good pot now, but yeah, so we should be okay for speakers for a little while yet. So that's good. There are other meters. I don't know if there's Pete in, no, but on Monday and Thursday evenings is the Reach Out and Touch Space get-togethers.
Pete's at Liverpool AS.
Yeah, Dave Galvin's involved in that, isn't he?
Yes.
So he's helping Pete out with that. Yeah.
Yeah.
Yeah, and then Sunday evening, Stargazers Lounge, you've got the Stargazing, and this weekend they've got Mary McIntyre's going to be talking to them. I can't remember what she's talking. Oh, Women in Astronomy. So if you want to catch up with Mary's talk, that's this Sunday. So go on to
It's a very interesting talk, highly recommended.
So go on to Stargazers Lounge forum and you pick up the details. It's completely free again. Mike, gospacewatch.co.uk. Do you want to tell people what's up and coming? Because you've got one tomorrow night, haven't you?
Yeah, we got one tomorrow night. It's Lee Fletcher of Leicester talking about Juno to Juice, about the new ESA icy moons orbiter of Jupiter. I'll go through the ones in May if I can. I've got Wednesday the 5th of May, we've got Dr. Hannah Sargent of the Open University with Mining the Moon. 26th of May, we have Robin Hay, head of launch at Skyrora from Scotland to Space. And Wednesday the 2nd of June, we have Stephen Eisel, who's Vice President of Virgin Orbit, total TBA. And on Wednesday the 23rd of June, we have Ben Evans, spaceflight author, with a talk entitled An Experimental Flying Machine.
Oh, competition there.
Oh.
Okay, thanks, Mike.
Thank you.
Okay, so as I find out these events that are going on, I pop them in my diary. So as you can see, it's filling up really, really nicely. And new one on there on the space dates was the anniversary of the Ingenuity's helicopter's first flight on Mars. So that was to put in there yesterday. Freely available, so go to my website, star-gazing.co.uk/diary. You can download the Team Up app and take it around with you. Okay, so it's completely free. So the next meeting's on the 4th of May. Catherine Rayner Evans going to be talking about exploring astronomy in space through philately. And then the 18th of May, I've got Paul Money again, our favourite enthusiastic astronomer. He hasn't given me a subject yet, but I'm trying to get to do something a little bit more practical. And he was talking the other night on Stargazers Lounge about taking images through a huge dob. So I think that's what I'll try and persuade him to do that. So an undriven dob doing very short exposures, and some of the images he's managed to get off there are really, really good.
Yeah.
So I thought that would be quite good for people to see.
Excellent.
That's one for Kath.
It is, yeah. I was going to say.
That's if your phone's working.
Oh, don't! It's with I've got to tell you, it's with a repairman at the moment. I think I'm having a nervous breakdown, thinking, is he dodgy? Is he going to bring it back? Anyway.
So is it the phone itself, or is it the phone itself rather than the charger?
It looks like the battery, because I borrowed a charger, but he looked at it and he said the battery was down to about 70% of its life, and I've got a cracked screen, but he's going to repair it and hopefully bring it back tonight.
Oh, good. Hope so. Good.
Yeah, we'll get a nice one of the moon again tonight.
Not here, it's full cloud, Roger.
Yeah, same here as well. A huge black cloud coming over here.
Yeah.
I think I've come into the wrong club because it says Virtual Astronomy Club. This is not the Eagle Spotting Club.
Dave.
Oh, my apologies.
You don't get any better, Dave.
Okay, sorry about that, folks. I'll change my background at some point.
Hi, Dave.
that was a bit rehearsed, wasn't it?
Almost convincing, Dave.
How long have you been working on that?
Update no notice.
I actually went to bed last night.
We don't.
I thought about it last night.
We've got Phil who's going to talk about the history of the space shuttle. Do you want to say anything about that, Phil? I saw you were in.
Yeah, just really that it's because it's the anniversary of its launch this year, 1981, and the 10th anniversary of its decommission end of July. This is sort of bang in the middle of the two anniversaries to sort of bring the two together.
It doesn't seem like...
No, it doesn't.
It doesn't seem like 10 years ago that Kev and I were in a field covered in flies trying to catch the space station and Atlantis just after they'd undocked. from
got
it.
it.
Remember that, Kev?
I do. We got it.
We did get it. A very, very small shuttle, but yeah.
Don't spoil somebody.
Dave, was that a Wednesday evening by chance?
I can't remember when it was, but I think it's about 20 minutes after undocking.
Well, yeah, it sounds possibly the Wednesday. We have our observatory even on a Wednesday.
It transited across the sun, so
yeah. This is a solar transit. Sorry,
it's a solar transit. It was only a few miles up the road from me, so it wasn't too bad.
Yeah. No, I was thinking of something else. We watched a live launch via NASA TV at 7 p.m. on a Wednesday evening. And then we obviously calculated it earlier that it should come up over Britain about 20 minutes later. And in the twilight sky, we saw the ISS. We saw the space shuttle rising over the horizon. But right behind it was this orange. It looked like an orange satellite. It was the rockets, the big orange tank.
Fuel tank.
And then it came right across the sky. Then went into shadow. But fantastic sight,
They're so clearly different in colour, weren't they?
Certainly was. It was like looking at Arcturus and Sirius, or Venus, brilliant.
So looking forward to Phil's presentation on the space shuttle.
And I borrowed some pictures from Dave. Thanks for that. So able to show that quite clearly during the presentation.
And then 15th of June is our last meeting before the summer. So end of term party. So nobody's sent me any suggestions yet. So any suggestions for what we should do? John, I think. Well, we have had a suggestion, haven't we? That John gets his guitar out again.
Everybody said sing along.
Show me the way to go home.
Any suggestions? Throw them forward. Everything's up for grabs. So just make it a fun evening before the summer.
Can I just mention a quick one, Dave?
Yeah, go on, John.
If people have got nothing to do on the Wednesday, the 28th of April next week, I'm doing a talk on the anatomy of the Milky Way. So I'm going to try and cover about 3,000 years in an hour and explain what we know about the Milky Way and why we know where we are, etc., etc. So there we go.
Who's that with?
7:30, and that's Bedford Astronomy.
Oh, right, that's Bedford Group. Okay, yeah, I'll get the details and I'll pop it in the diary because I get their details through. Okay. Excellent. So July and August, we're having a break, but 28th of September is when I've sort of penciled in the start of the club. It's not the usual first and third Tuesday, but that's one I can hit for that month. So 28th of September, pop it in your diary. Okie dokie. Oh yes, and when I get time, I will try and get another gastropub going, but at the moment life's just mad, absolutely hectic. So but I will have a look out and I will announce it when I do get time to do one. So that brings us to tonight's meeting, and there's not much cake. I haven't seen much cake about in people's windows there, but we got Julian, who's going to be giving us a talk all about crazy experimental spaceships. So, Julian, if you'd like to share your screen, and if everybody else can mute, please, that would be fantastic.
Righty-ho. Is that coming over okay?
Fantastic. Excellent. Okay.
Right. Very good. So, I was sort of inspired to write this talk by watching a YouTube video, as sometimes happens. I was just surprised how many crazy spaceships people have come up with over the years. So these are ideas that are mostly practical, and you could probably almost buy them off the shelf if you've got a big enough shelf and a big enough budget. So if you want to go and tour the universe, or at least tour the solar system, or in some cases the universe, then these are ways you can do it. So, if that's the sort of thing you want to do, go and visit distant planets and see the sights around the universe, then these are some of the ways you can do it, perhaps. Well, at least we'll see. So let's start with how far have we got? How far have we explored the galaxy? And to cut to the chase, not very much, and not very quickly. So if we look at the things that have actually left the solar system, there's about 4 or 5 of them, depending on how you count leaving the solar system. Voyager 1 is the furthest away at 152 AU. So that's 152 times the distance from the Sun to the Earth. So well outside the solar system. But we've also got Pioneer 10, 11 and Voyager 1. And New Horizons is also heading out that way at about 50 AU. So got a bit of catching up to do. But if we look at where they are, so the nearest star, 270,000 AU. So you can see still got a little way to go before they get anywhere near that. And if we look at actually where they will pass, Voyager 1 will pass within 1.7 light years of Gliese 445 in 40,000 years. And that's one of the quicker ones. So the Pioneer 11, Aquila, Lambda Aquila in 4 million years, Pioneer 10, 90,000 years, and none of them getting very, very close. So, the current technology is really not up to exploring the galaxy as such, and struggles even somewhat with exploring the solar system. I mean, New Horizons took 10 years to get to Pluto. So, that's doable with if you make somebody the right offer, but otherwise not. Now, I have to give a warning here, because this is a bit unusual. I've gone and included something that I normally don't include in talks, and that's mathematics. So I'm just watching to how many people switch off. Okay, nobody so far, that's good. So there's some maths coming up. It's not, well, I don't think it's particularly hard maths, but it does help sort of explain at least the basis of what we're going to be talking about. So this is how rockets work. I'm sure you all understand that. You shoot stuff out of the back, which is the exhaust, and that shoots the rocket forward. So that's not the maths bit, by the way. So that's Newton's third law. For every action, there's an equal or opposite reaction. So if you shoot something out the back, your rocket shoots forward. Now, this is where the maths does come in. This is Celoska's rocket equation. And this is the sort of thing that all the rocketry is built around, is this one equation. And what does it cover? Well, there's the delta V over there. So that's how much you can change your speed. So you need to change your speed every time you want to leave orbit, you want to enter orbit, you want to slow down when you come to a planet, you want to leave a planet. That's all those sorts of things. And it's really quite a straightforward equation because there's not that much in it. So what does that ability to change your speed depend on? Well, it depends on, the crucial thing is this thing here. How fast is your exhaust? How fast are you shooting stuff out of the bottom of the rocket here? That is one of the crucial things. So the faster you can shoot exhaust out of the back of the rocket, the more you can change your speed and the more you can basically do things. So delta V is kind of what everybody relies on in rocketry. The other two bits are not quite so interesting. So there's the initial mass of the rocket, which is often called the wet mass, because that's got all the contents of the rocket, the fuel and all that stuff. And the final mass is what you end up with when you've used up every ounce of fuel that you've got left over. But this bit is kind of less significant because there's this thing here called a log. I don't know how many of you did logarithms at school, but they tend to make things smaller. So whatever this quantity comes out, this makes it smaller. So you're really very dependent on this exhaust velocity. The other really key thing, and I'm going to use this quite a lot, so I thought I'd spend a slide or two just talking about it, is, there's a quantity called impulse, which is the force times the time. So the force is kind of the thrust. The thrust of the rocket is the force, and the time is how long the thrust lasts for. Now, that is a quantity you can talk about, but as far as efficiency goes, there's an actually much better one, and that's called the specific impulse. So you take that impulse, which is the force times time, and you make it specific. So by making it specific, in this case, we're dividing by the mass. So, and actually there's a G thrown in there as well for sort of historical reasons. So this equation actually gives you the efficiency of your rocket. So a better ISP, specific impulse, is a better rocket. So if you just remember that, bigger numbers are better. So as the specific impulse gets bigger, your rocket gets better. And you can think of it as this 1 kilogram or 1 pound or 1 ton or whatever you want to work of fuel, how many seconds can it maintain that thrust for? So it's actually something that's given in seconds, so which is a bit weird, but just go with it. So specific impulses are given in seconds, and you can think of it as how long could you hover a rocket for if you had 1 unit of fuel. Now you can actually do some mathematical derivations. After this slide, there's only one more formula in the whole talk, which is a bit of a doozy, but I'll come back to that. So you can actually substitute this in. So where we have the impulse here, we've already got that force time time, so you can put that in place. You can, wherever you've got I, you can put F and T. So that's okay there. You might also remember that F equals ma, that's Newton's law, which is mass times acceleration. So you could replace F with ma here. And in fact, if you're on the surface of the Earth, the acceleration is due to gravity, which is g. So we drop that in there, and you can see ISP there, and you can actually then cancel those things out, and you're left with just time. So that's why ISP is given in time. We're nearly done with the maths. Is everybody still there? Oh, okay, we lost about 50p, but I expect. You can also put it in terms of the exhaust velocity, and you can also put it back into this equation. This is delta V again, and this time we've got specific impulse. But anyway, all that goes to say is that specific impulse is really one of the crucial things about a rocket, how efficient it is, how efficient the engine is. I just mentioned this G0. This was included by Werner von Braun and his team when they were working on this. So you could get rid of that G0 entirely, because that's often how you measure specific things. You just divide by the mass. But because Werner von Braun and his team, when they started working in the US, they were working in metric. Americans were working in imperial measures. So if you drop this G0 in and you measured it in meters per second for his team and feet per second for the other team, everything, it still came out to the same thing. Whatever your specific impulse was, it always came out to the same thing. Right, that's all the maths, pretty much. One more slide, but not till nearly the end. So let's look at some specific impulses. Let's get a feel of what is a good propellant and what isn't. So perhaps the very first one that anybody's ever used was gunpowder. And this has a specific impulse of about 80. So kind of like with a kilogram of gunpowder, you could actually hover a rocket for about 80 seconds. That would give you the measure of sort of how efficient it is. And we know you've seen rockets on fireworks night and exactly how good they are. They're not too bad. But we can obviously do better. We've improved a lot since just using fireworks. So let's look at what some of the more modern ones. Solid rocket boosters, SRBs, which use this compound called ammonium perchlorate composite propellant, APCP. They've got pretty good thrust, 12,000 kilonewtons, but an ISP, this is the efficiency factor of 242. So that's quite a lot better than gunpowder. It's about 3 times better, in fact. The trouble with these solid rocket boosters, as I'm sure we'll get to hear in the later talks in the year, is that they are sort of fire and forget. Once lit, you can't unlight them. They just burn until they run out. But they're quite good, 242 ISP. They're not quite as good as the liquid fueled engines, such as on the Saturn V, which was a mixture of kerosene and liquid oxygen. So a typical engine on the Saturn V, 35,000 kilonewtons, but an ISP of 263 to 304. So it's a little better than SRB, but you know, getting up there. And these two numbers, one is when you're on the surface and one is when you're in space. Things change a bit as you go up through into the vacuum of space. The Space Shuttle does even better. Its main engine, which is almost the perfect fuel, which is liquid hydrogen and liquid oxygen, and they get a fairly good thrust there. But we're up into the 300s to 400s, again, on the surface of the Earth and in the vacuum. So if we drop that into a nice slide here, so you can compare them. There's gunpowder, Here's an SRB. This is the liquid oxygen kerosene, or in the second stage, it's even better. And the space shuttle, you can see also sort of somewhat better, depending where you are. It's not fantastically better, but it's better. And they've all got their associated thrusts. So thrust is something we're going to come back to because it's also quite a vital component. However, you might think that's really good, 452, but if you compare that to a turbofan on an airliner, they're getting a specific impulse of about 3,000. So what's going on there? Why are they so much more efficient than rockets? And you may or may not have guessed the answer, but they cheat, basically. So they're using a lot of oxygen from the air and only carry half the fuel mixture that something like the space shuttle has. So they're cheating quite considerably with the turbofan. Although there are other tricks they bring into play too. And this gives us this is a nice one I picked up from Wikipedia, showing you the sort of efficiency of these things. So these are, here we've got turbofan or with afterburner, ramjets, all these things, and the theoretical things. So there's Concorde, there's a 747. But you can see rockets, they're flat all across there. Doesn't matter what Mach number they're traveling at, they're always got more or less the same specific impulse. It doesn't really vary very much. Even with the space shuttle, once it gets into orbit, it's not that much more efficient. So you might try to do something as a hybrid. So we had a talk on Skylon, I forgot where, Michael's club, I believe. So this is a hybrid thing. So it uses sort of jet engines for the first part of the atmosphere, and then it switches to rocket motors. And you can see here the ISP starts off really good. We've got a really good system here that the turbofan is really very, very efficient. But then as it gets up the Mach numbers and also gets up in altitude, it can no longer use the oxygen from the atmosphere because there just isn't enough around. And its efficiency tails off quite considerably back down to that of a rocket motor. So that's one of the issues you've kind of got with these things. You can do a lot better, even nowadays, you can do a lot better. There's electric rocket propulsion, and this is using ion engines. In this case, you have a fuel that comes in here, you hit it with some electrons, you make it charged, and then you accelerate it with a large electric field. And these ions of typically something like xenon are shot out of the back at enormous speed because you can accelerate them through enormous voltages and shoot them out. You do have to have this neutralizing electron beam here to cancel out the charge of these ions. Otherwise, they just swarm around and come back and hit your machine again. So ion drives, they have a remarkably good ISP. So here we are, 3,000 to 10,000. So that's even better than a turbofan. The trouble here is the thrust. So 600 micronewtons is not really going to wow anyone. You're not going to get that featuring on Top Gear. So, I've got that topic wrong. Should say ion engines. It's only the second time I've given this talk. I'll have to correct it. Right, so what's good about them? They have a really good ISP. They're extremely efficient. So some of them are up to, say, 10,000 ISP, and it just needs electricity. So however you can get electricity, solar panels, batteries, whatever you want to use, that's really all you need. So in some cases, it's almost like a free ride. You need a store of propellant, but because you shoot it out so much, you don't need that much of it. The not so good is the 0 to 60 speed of these things is about 2 days. So you're not going to have any violent acceleration for these, but they can keep it up for sort of months at a time. And it's proven technology. They have used them on satellites. So you might think this is great, but it's still got some issues. It's really, really slow. But if we put it on here, I also put a scramjet on there, which is a supersonic ramjet. Here we have ion engines, and there are some versions that even are up to 12,000 ISP. So fantastically efficient, but you're never going to lift anything off the surface of the Earth because their thrust is just pathetic. But weren't you promised crazy freaking spaceships in this case? And there's a selection of spaceships. I should have included Dave's, which has got a fabulous one. So there'll be a quiz at the end. So just have a look at those, see how many of those you could name and what genre they performed in. So yes, you were promised crazy freaking spaceships. So let's get on with some of them. And quite a lot of these revolve around the nuclear option. So nuclear power and spaceships, yeah, what could possibly go wrong? Well, quite a lot actually, but let's start with the kind of the simplest. So these are nuclear thermal rockets. So these are really, really simple. You've got a nuclear reactor, which is probably, they are reasonably simple in concept at least. So this is like something packed full of uranium, and you've got a fuel here, such as hydrogen, and you start up your reactor, and it gets really, really hot, and you put fuel through it, and the fuel obviously gets very hot and expands and goes shooting out the back as a very hot jet of fuel. So this is really fairly straightforward. We know how to make reactors. There's plenty of reactors around. We know how to get liquid fuel. Putting them together in a rocket, a little iffy, I have to say, but it was certainly considered. And there was this Project Rover, which was the original one done in the 1960s, I think, in the USA. And also this thing called NERVA, which is a nuclear engine for rocket vehicle applications. So I think some of what was driving this was the possibility of having ICBMs, so intercontinental ballistic missiles, powered by nuclear rockets. You know, if they were more efficient and they could get the stuff to the target faster, then, well, why not? Because you're going to be unloading nuclear warheads on wherever it was going to anyway, so it doesn't seem that tragic. I think I'll skip over the next one. That's but you know, this really simple thing, just a reactor and a tank of something like hydrogen, and yeah, we're getting really much better performance. It's not nearly as good as an ion engine. It's not as good as a turbofan, but it works in space, and it's actually been proved. They've actually had these things running in the deserts of probably New Mexico or somewhere like that. So NERVA is certainly a possibility. I did find this image on the web that you can actually buy a kit of it. So there you go. I think it's only an Airfix type kit. I don't think it really comes with nuclear material, at least I hope not. So what's good? They're much better ISP than chemical engines. So, you know, it's much better than the space shuttle. It's relatively straightforward. As long as you know how to make a nuclear reactor, which certainly people do, then there's not very much to it. And it's also been tested, so we do know it works. And they had, I think, about 6 or 7 actually active test engines that none of them actually went anywhere. They just sort of measured the thrust and said, you know, this will work. Things that are not so good, if you've got staged rockets, and pretty much everybody has staged rockets, so you have stages 1, 2, and 3, you're going to be there dropping a reactor into the sea at some point. So they did consider that. They were looking at these for, they were kind of looking at it for the successor to the Apollo at one point. This was mid-60s before Apollo had actually gone anywhere. So they were saying, well, you know, once we've got Apollo going, can we do better? Yes, we can. We can do a nuclear reactor. But we've got to at least drop the first stage into an ocean. So what's that going to do? Where's it going to end up? What's going to happen to it? Is it going to stay intact and all that sort of thing? Probably not going to be taken terribly well today, in today's climate, that dropping reactors into the ocean is probably not going to be something that you're going to get away with. So they're probably not going to be seen anytime soon, even though they are much more efficient. And of course, you've got things like fueling and handling. Anything to do with radioactive materials floating around is going to be a bit hazardous. But if you thought that was hazardous, what about the next one? So this is cutting out the middleman, and these are called nuclear saltwater rockets, and were envisaged by Robert Zubrin of the Mars Project. Now these are, I have to say, quite, in some ways shocking and terrifying, but they are phenomenally efficient. So what do? You have a fuel tank here with nuclear salts. So this is like uranium dissolved in a liquid, uranium bromide in this case, and you have these baffles in your tank that are actually neutron absorbers. So they stop the rocket from sort of exploding prematurely in an atomic bomb sort of way. So they keep the fuel separate until you send it out here, and then there's no longer the neutron absorbers. So suddenly the fuel reacts together, much like it does in a nuclear reactor, or in the worst case, in a nuclear bomb. And it just gets really, really hot, really, really quickly. And you get this incredibly force. And they also inject water into it, so you get even more. The reaction heats up very quickly, and then you get a lot of steam from this water, and you get enormous amounts of power from this sort of thing. So depending on what you use, if you use reactor grade materials, you can get a reasonably good ISP. If you go to weapons grade material, then you can get even better. But it's a little tricksy somewhat, shall I say, because you've got to send this stuff out fast enough that the nuclear action happens somewhere in this nozzle or even a little bit further out. And if you don't send it fast enough, then the nuclear action sort of moves back up the bell and would sort of go inside the rocket and presumably be somewhat hazardous at that point. So a fantastic concept. But, you know, if you thought having these nuclear electric rockets and things like that were hazardous, dropping nuclear reactors in oceans, these just take that a whole step further forward. So what's good about them? Really good ISPs, up to 10,000. So you're getting into, that's with weapons grade material. So you're getting into sort of the ion drive ability there. Again, a fairly simple design. You don't need any particularly complex moving parts. You do need a fairly efficient pump that pumps this stuff out fast enough that it doesn't come and consume you. You have an enormously high exhaust velocity. So if we go back to the original rocket equation, which had delta V depending on the exhaust velocity, this comes in really high up there. So, you know, with 10,000 seconds. The not so good is, to say, it's a little lively if you don't get your things perfectly balanced, then it will come back and sort of consume the rocket. It's highly radioactive output. You've basically got a sustained nuclear action happening in the nozzle of your rocket. So you're spraying radioactive material out at these super high speeds. It's about 4 million meters per second it comes out at. So you're spraying radioactive material far and wide as you use them. And so, yeah, I say it has to burn in the nozzle, and if it gets too close to the nozzle will vaporize. If it gets too far inside, the whole thing will vaporize. But it has been considered for sort of deep space maneuvers because it's so efficient, and because the exhaust comes out at such a rate. It's highly radioactive, but it spreads out very, very quickly, and so within a few minutes. Providing you're not standing within the exhaust, the radioactive stuff is spread so far and wide that it's not much worse than sort of standing in the cosmic ray bombardment in outer space anyway. So if you want to go to Mars or Jupiter or somewhere like that, this is probably a very efficient way of moving around because you only need one component of the fuel, and it's extremely good at that sort of thing. So if we put that on our list, nuclear saltwater rockets, way up there, way beyond anything the Shuttle can do or Apollo. as an efficient means. So great stuff. Now, if that's not scary enough for you, there's an even better way to use nuclear power to get a rocket. And this is, well, why don't we just use atomic bombs? We've almost got them with the nuclear saltwater rockets, that they are sort of a sustained nuclear action. Well, why not go the whole hog and have a nuclear bomb, you know, like this. Here we are, fire one out and boom. And this is the basis of Project Orion. I mean, this is quite staggering that people could actually consider this. But when you see the benefits, you might even be tempted to think, well, you know, we might even consider doing that. So this is the principle behind it. You have this rocket up here full of atomic bombs. You have this system is a sort of a magazine of atomic bombs that drops them one at a time. There's this pink thing here, which is the pusher plate. And what happens is it ejects an atomic bomb out there, which then explodes, gives off an enormous explosion. You know how powerful atomic bombs are, and boosts the ship up. You've got all this sort of springs and compression stuff to try and absorb some of the explosive force, and you've also got this very thick thing called the pusher plate that will slowly vaporize over time because you're subjecting it to atomic bomb after atomic bomb. And just to put that in context, you know, there's maybe 300 nuclear explosions needed to get from Earth surface into orbit. And here's one of the concept vehicles. So you've got this propellant magazine here, which is full of these atomic bombs. It just clicks around, drops another one down this tube, fires it off, absorbs the impact, and launches the machine up. So this is Project Orion. There's lots of stuff on the internet about it because it's mostly declassified, apart from some of the more tricky bits. And here's some of the film they did. So this isn't actually using atomic bombs. This is using regular explosives, but using the same sort of technology. So there you go, launch and then an explosion, and you can see it sort of flies up quite well there. I think this is just, I don't know, gunpowder or TNT or something like that. So they did a lot of tests on this, and the concept is absolutely sound. You can certainly power a spaceship by just detonating nuclear bomb after nuclear bomb. So why might you want to do that? Well, the payoffs are absolutely extraordinary. So here's the Saturn V. We can get 130 tons into low Earth orbit with the Saturn V, or 2 tons to the moon. So that's the sort of possibilities for the Saturn V that we're all familiar with. Here's the range of possible Project Orion spaceships that they came up with. I have to say none of these were ever built, but they were certainly on the drawing board and went into a lot of concepts. So they had various scales. So there was those that went to the moon, those that went to Mars, going to Jupiter, and we also had an orbital test and the absolutely terrifying orbital battle station. So what are they capable of? So the lunar ones, they contain about 800 of these, in this case, 0.03 kiloton bombs. But the payoff is you get 300 tons into low Earth orbit and 170 tons to the moon, or 80 tons to the Mars. When you think of, you know, what we're doing at the moment, Perseverance, somewhere around a ton, is it? Something like that. Here you are, dead easy, 80 tons. You can take 80 Perseverances. And that's on the smallest of their concept ones. The Mars and beyond, so same number of bombs basically, but bigger yield at 0.14 kilotons, 1,600 tons now. You can lift off the ground into low Earth orbit, 1,200 tons to the moon, and 800 tons to Mars, so 10 times the amount. And the Jupiter one, even bigger. But yeah, if you want to go to the moon, you can take 5,000 tons of a payload, or 5,000 nearly to Mars. And Jupiter is quite easily obtainable. But they didn't stop there. There was even bigger versions of this considered. So there's the Super Orion, 1,080 bombs, 3,000 tons each, 400 meters across, 8 million tons it could lift, this thing could. So that's, you know, a reasonably small city you could get into orbit with one of these things. So, you know, that does make you, you know, if you're at all interested in rocketry and things like that and going into space, you suddenly think, well, would it be so bad if we, you know, nuked a small patch of the Earth just to get 8 million tons into orbit? Yeah, it probably would be actually, but you do waver a little. Another version they had was the sort of the maxed out version, which was called the Momentum Limited Orion, and this could get to Alpha Centauri in 133 years. For only 400,000 tons in this one, so you know, peanuts really. But when you're carrying something of that sort of weight, everything else in rocketry, you're trying to slim it down to the tiny, you know, the lightest weight you can, because you're always caught out by the rocket equation. But in this case, you've got as much weight as you want. You know, you want to pack a gym, fine. You want to have a swimming pool in your rocket? Absolutely, you know, because there is so much efficiency and concepts here to lift these things into space that fabulous. So yeah, very good ISPs, fairly simple design if you know how to make atomic bombs. And I have to say, Freeman Dyson was one of the people behind this, and he actually produced a system for mass producing atomic bombs, because he said, well, we're going to need several thousand of these things if we're going to do it. So he had a theoretical way of producing just a whole load of atomic bombs, which is still classified, I believe, to this day. He had this production line. So you've got a huge lift capacity, say in the biggest you can lift a city into space, basically. The not so good is the nuclear bombs. So you're going to have quite a number of these nuclear bombs going off, certainly at ground level to begin with, before you get up into space. That's probably going to upset a few people, not in my backyard, I guess. And highly radioactive output because it's nuclear bombs. So yeah, crazy, but there you go. What about going to the next step? So we had fission bombs. What about fusion, which is the more perfect? You know, you get a lot more bang for your buck with fusion over fission. So this was looked at by the British Interplanetary Society in their Project Daedalus, which Alan Bond, who is part of the Skylon, or in fact, I think the leader of the Skylon, was part of the design. It's a big old beast. You can see it there next to a Saturn V. So a huge thing that could cruise. They were aiming to go to Barnard Star because they thought it had a planet back in the, I think it was the 70s or whatever. So they thought that was a reasonable target to go to, and this is the way they could do it. And I have to say, I don't think you can actually do this, or nobody's actually done this in practice, but this is the idea. You drop a small pellet of deuterium and hydrogen, I think, and then you hit it with lots of electron guns, which has the effect of heating it up and compressing it, and you get a burst of fusion that expands rapidly and gives you your power. So it's that sort of thing. And you have a constant stream of these. These are sort of the size of a few millimeters, I think, but you just fire them one after another, hit them with these electron guns and shoot them out. Get this big explosion. So this is one of their concepts with the electron guns and all the other bits and the fuel tanks and everything else that they could take on board. I think it was superseded by another one, Project Icarus, which, if you know your Greek mythology, probably works out well. I don't think that was quite completed. These are all just sort of drawing board designs. Nobody has built one of these, obviously. The good, they can get up to about 12% of the speed of light. The specific impulse is very good. The Project Daedalus weighed 54,000 tons, of which 50,000 was fuel. It would be built in low Earth orbit and then sent off to Barnard Star, and they reckon they could get there in about 46 years. So, yeah, not too bad. Not so good. Well, it's very large. You need something to get all that material up into orbit in the first place to build something much bigger than the Saturn V. That's going to take a bit of the thinking. Nobody else is thinking back to Project Orion, and no, you shouldn't be thinking that. And there may be better targets now. The idea of going to Barnard Star, well, we know there's planets around Alpha Centauri now, which probably get to even quicker. And I say Project Icarus was the follow-up. Another way that was thought was the Buzzard Ramjet. So much like a ramjet on Earth, a ramjet works by you shoot an aircraft through the air as fast as you can, and if it's going at a certain speed, you're actually ramming stuff into the engines so quickly that you don't need any of these compressor blades or anything to do anything. The fuel, the air is coming in so quickly, it's sort of doing its own compressing. But ramjets don't really start working until you're about Mach 2 or 3 at minimum. And scramjets, obviously, the supersonic version of that, they start about Mach 5. That's where the air comes in at supersonic speeds rather than just regular speeds. So the Buzzard Ramjet is a bit like that, but taken out into interstellar space. You go whooshing off through the space between stars, and you might think it's a perfect vacuum, but actually there's quite a lot of stuff floating around. It's very, very low density. But if you're going fast enough and you've got a big enough scoop, you could actually scoop up hydrogen as you go. And there are methods where you sort of ionize the hydrogen ahead of you with lasers, and then you have a magnetic field that goes way beyond this big scoopy dish. So you can collect lots of hydrogen that way, funnel it down, compress it, and put it into the fusion engine at the back, and you've got this interstellar ramjet that Robert Buzzard came up with in the 1960s. Be a great concept. There are a couple of issues with it, which I'll perhaps talk about. I'll leave them to the good and the bad. So this is the sort of idea. You have this big hydrogen scoop. Some of it is actually material, and some ways it's just sort of magnetic fields that's scooping it up. You feed the stuff through here and into the fusion reactor, which is safely at the back. And once it gets up to speed, it sort of scoops up its own fuel as it comes along. And there are lots of other fusion options besides that. I haven't really got time to go into all the concepts, but just some of the names are enough to delight you. I like muon catalyzed fusion or ultra dense fusion, antimatter torch engines. They all sound just lovely concepts. They're probably all quite lethal, but anyway, that's the way you can do fusion. So there's lots of ways to do fusion, none of which have yet proved to work. So they're very good, fantastic ISPs of 100,000 in some cases. Again, it's a fairly simple design and not many moving parts, very high exhaust velocity because of the fusion that's output. They're not so good. How do you stop these things? Once you've got going and you're funneling all this hydrogen in, if you switch it off, you're just going to coast along. And if you're going at 0.3 of the speed of light, your stopping distance is going to be quite considerable. And you can't really just turn it around because then you lost your scoop. So you either have to store enough fuel to do braking, or I don't know. I don't think that's been thoroughly thought through. The other problem is it turns out we're not in a very good place in the galaxy. We're in a position where our sun and solar system is in a sort of bubble that's been blown out by a supernova many, many years ago. So that explosion has sort of moved a lot of the hydrogen that tends to be floating around the galaxy out of the way. So we don't have a lot left over. So it's not a great place to go zooming around and collecting hydrogen, because there isn't as much around in our neighborhood as there would be in other places. And the other problem is you need to get up to speed. You've got to get up to this speed where you're collecting enough hydrogen to begin with, So there are some issues with that. You need some sort of method to get you going to begin with. So that's certainly one way you can do it. Fusion is really hard as well. Nobody's really managed to do that in a controlled way. You know, a fusion bomb is about the best we've done, and that's hardly controlled. Other ideas, Project Starshot. You've probably heard of this. It was in the news a few years ago. Stephen Hawking was involved in it. This is a nice little video that they released. So the idea behind this is to send very, very, very tiny spaceships off with these huge sails, and they don't really have any engine. Well, they don't have an engine at all. What you do is you hit them with the combined power of all these laser systems. So you shine a vast quantity of light at them, and that accelerates them at a truly stunning acceleration rate. And then you dispatch another one, and you hit this one with the lasers, and off it goes. So that's the breakthrough Starshot. This is still ongoing. It has Russian backing. Russian oligarch or someone has put a lot of money into it. Say there we are. You accelerate at 10,000 G. So not really good for humans, but okay for solid things. 1 terajoule of laser power. That is a truly staggering amount. They reckon 10 minutes of that is enough to accelerate it up to about 10% of the speed of light, I think. And because of the hazards, they're going to send sort of 1,000 chips, basically. So you mass produce these chips down to this sort of size and fire off 10,000 or 1,000 of them, all with this system. And some are going to make it and some are not. And it's you know, kind of the law of the jungle, who gets through. So what's good about that? Well, the good thing is you don't need to take any propellant at all. So, you know, ISP isn't even considered. You just hit it with this huge beam of laser power and off it goes. Cheap to make. Obviously, they're sort of integrated circuit sized. So, you know, really, really small. And you can send lots and lots. So if some don't make it, some have faults on the way, you know, maybe you only need 1 in 10 to get through, and that's still 100. The not so good, and I don't know how they're going to get around this. I'm sure they've got some very intelligent people. They did have, let's say, Stephen Hawking working on the project, or at least backing it. What stops you vaporizing the chip? If you're going to hit it with this 1 terajoule of laser power, why doesn't it just vaporize into nothing? So that's something I'm not too clear about. Another problem is interstellar dust. If you're going at 0.2% of the speed of light or something like that, as I said, it's not a perfect vacuum out there. Every so often you're going to run into little grains of stuff. If you're going between here and Alpha Centauri at you know, a fraction of the speed of light, but they're not even bullets hitting you. They've got so much energy hitting you that they're going to vaporize a small chip very easily. So you've got to think of that. So probably the loss rate is going to be quite staggering. And I also have a concept. The idea is that they fly past Alpha Centauri at 0.2% the speed, 20% of the speed of light, and they take as many pictures as they can as they go past, which, you know, is not very long, and then they send the data back. But I'm not sure how you can send data back from a tiny chip, how you can get enough power to actually send it back so we can pick it up at 4 light years distance from this, you know, something about the size of your thumb. Again, they've got some very clever people working, so maybe they can work that out. And as I say, you're passing the target at 0.2C or something like that. So maybe your aperture speed has got to be pretty swift to actually catch anything at all. And it's probably all got to be programmed ahead of time. You're not going to be able to, you know, if you think controlling Perseverance or Curiosity on Mars is a problem, certainly trying to control something at 4 light years distance is even harder. One other concept before I hit you with the big one is the power of light. So this is photon drives. So the simplest case is you have a reactor that's glowing white hot. So it's shooting out a lot of light. And light has a momentum. it comes out at the speed of light, as you might have guessed, so your exhaust velocity is very high, but they're not particularly efficient at providing thrust. So that's the simple case. You just let your reactor sort of basically overheat and glow white hot and shine it out the back. If you're a little more liking living on the edge, then you crash together positrons and electrons and you annihilate those and you get gamma rays coming out. So you get even more noxious rays coming out of the back, and you get a bit more thrust from that, but it's extremely deadly substance coming out of the back. So the specific impulse at this is basically speed of light. So that's the exhaust velocity. So it's a huge specific impulse, and it needs no fuel because you're just shining light. Anything that you can get to glow is good. The trouble is, light is, as it says there, well, light, it's very light, so you don't get a lot of mass kicked out of the back, so you don't get this action and reaction. So it's really quite inefficient. And consequently, you get very low acceleration. And as I say, if you're going for the extra option, the exhaust is fairly deadly. So we can put all those on here. So yeah, ISP, the photonic drive is the absolute, whatever you want to call it, with some of these others also fitting in very high levels. This is a log plot, by the way, so everything goes up by factors of 10. So it makes our current efforts look really poor. But we're not done. There is one last thing, the warp drive. Star Trek, yes. This came about by Miguel Alcubierre, who was a PhD student at the time. He was working at San Diego, I think. So he was working under his supervisor, messing around with general relativity equations and doing that sort of stuff, which he's done ever since, actually. He's a well-known figure in general relativity. But he was watching an episode of Star Trek, as I'm sure we all have. And he thought, well, they've got this warp drive. How hard can it be? So he played around with the general relativity equations and sort of turned them on their head. So here's the last equations one. So this is general relativity. Do not mess around with these equations. They are horrible. But this basically tells you how space curves, and this tells you how matter behaves. And there's a lot of nastiness hidden behind those symbols, let me tell you. But usually what people do in who are messing with general relativity is they say, well, what happens if we plonk down a black hole here? How does that warp space, and what does it do? What if we have a big star? How does that move things? What about the Earth? How does that affect gravity? He came at it the other way and said, well, what if I want to warp space in a particular way? I want to actually have this warp bubble that Star Trek has. How can I do that? So he sort of fiddled around with this side of the equation and tried to get space to warp. And he actually managed that. If I just go back to, there we are, there's his paper published in 1994. Yeah, there we go. So he worked on these equations and went to his supervisor and said, I've come up with this idea for a warp drive. Do you think I should publish it? Will I get laughed at? Or, will everybody take me seriously? Or, what will it do to my PhD if I publish this? And his supervisor looked through the equations and said, well, I can't see anything wrong with them. So yeah, why not go ahead? And, sort of fame and fortune has been his, well, I don't know about fortune, but certainly fame. He is often asked to speak at science fiction conventions based on all of this. So anyway, the basics of it, if I go back here, this is what a concept of his spaceship might look like. And what it is this warp bubble in space. So you sit here in this flat bit, and this flat bit is regular space as far as you're concerned. There's nothing freaky about it. It's just like being in space. But the equations are arranged such that you get this area in front of you where space has all been contracted and squashed together, and the bit behind you where space has been expanded. So it's a bit like sitting on a rug or something like that, and somebody pulling the rug towards you, in this case towards Alpha Centauri. You just sit on the rug and nothing much happens to you, but you end up moving. And it has a lot of really interesting properties in that nothing happens much, probably nothing happens in this area that you're sitting. You don't feel any acceleration because you're not moving, you're getting space to move around you. So you don't get any of this violent G effects or anything like that. So if you can get it to work, you can almost go to any speed you like. You can certainly go to the nearest stars. You could go to the nearest galaxy. That is quite conceivable if this stuff actually works. There are a few hiccups. To get this warp bubble to occur, you actually need negative mass or negative energy because they're kind of the same thing. And in his first version of it, variant, you needed about 5 times the amount of mass of the universe in negative form to actually form this warp bubble. That's since been refined. Or other people took up the challenge and they got it down to Jupiter's mass of this exotic material, which we don't know how to produce, but if we could, you would only need a Jupiter's amount. But it was then taken up by Sonny White at NASA on one of their experimental things, and he played around with the equations and did some other sort of practical stuff, nothing that actually gets you a warp field, but he got it down to something he said would be about the amount of exotic matter that would weigh the same as a Voyager probe or something like that. So that's actually suddenly, if we could make that, that's not inconceivable amount of stuff, if only we knew how to make it. So yeah, these rings here would have that exotic stuff in it, and they would be shaping the warp bubble, and the ship would essentially stay stationary and the universe would move around it. Fabulous. There are some issues with it, as you might suspect. When you're moving along, everything contracts in front of you, so you can only actually see a tiny area in front of you. Everything else is absolutely blacked out. You can't see anything behind you or to the sides or anything like that. You've got this very tiny funnel. Another problem is that as you move through space, or space moves through you, everything tends to build up in a sort of wavy, bubbly thing in front of you. So you sort of accumulate all the stuff that your passage through space might have accumulated as a sort of bubble of stuff. And then when you stop, that goes shooting off. And there's an enormous amount of stored up energy in that, certainly enough to kill a planet. So when you arrive at Alpha Centauri, you probably better not be pointing at any civilized place, because you'd probably vaporize it on arrival. So that's one of the issues, that you could destroy what you've come to visit. The good stuff is it's the best bet to travel across space. You can get to Alpha Centauri as quickly as you like, basically. Theoretically within seconds, sort of thing, rather than years or whatever, depending on how much you can warp the space. It's inertialess, so you can accelerate. In fact, you're not really moving, so you can accelerate as fast as you like. And intergalactic is quite possible. People have done sums assuming that this all plays out and you can get to the next galaxy. There are things that are not so good. So you may destroy the system that you arrive at, which is not going to do. It's also not clear how you start and stop this warp bubble, because as soon as you start it, everything outside of your little enclosure, you cannot contact anymore. You are physically separated from it. So quite how you switch it off again, given you can't actually get to it, is not clear. And also how you start it up is not clear. And there's also issues that you probably produce a black hole behind you and this white hole type thing in front of you. So they're not very good. And you need this exotic matter. The other issue is that it probably allows time travel. If you can travel to Alpha Centauri in seconds and then back again, you've basically gone there and back in the time it would normally take 8 years. So you've gone back in time 8 years. So that probably is a hint that it's probably not going to be possible. But I think it certainly needs more thinking. stop press within the last few weeks. See, this is January 2021. This paper was produced, and so they've got a new version of this, and this one doesn't need exotic matter. This one can work with regular matter. I think there are still quite a lot of theoretical issues with it, even so. But, you know, we're sort of edging ever closer to being able to travel the universe and move as fast as we like. So with that, that's me done. The best way to travel, if you want to get off the Earth and you want to take a lot of stuff, the Project Orion is my best bet for that. But you do need friendly neighbours who are not averse to a few nuclear bombs going off in your backyard. If you want to shoot around the solar system, I really think these nuclear saltwater rockets are just fabulous. They've got huge capabilities, but yeah, not for in-Earth concepts. And if you want to go around the galaxy, you can't do better than the warp drive. So with that, I'm going to finish there. I'll leave this quiz up there, and you can all go have a go at answering those.
Marvellous. Thanks so much, Julian. Well, you've generated quite a lot of chat there now.
Oh, have I?
Yeah, there's been a lot of chat going on while you've been speaking, so that's great fun. Yeah, you mentioned at the beginning about having a big shelf for some of these things, but anyone who's got the Lego Shuttle would know you do need a big shelf for that anyway.
You certainly do.
So, yeah, if anybody's got any questions for Julian, you will be able to unmute yourself, but only unmute yourself if you've got a question for him. I know April did. Yeah.
Yeah, I had several questions, some of which were answered. But now my main question is, Julian hasn't mentioned any hybrids, and I was thinking about a skylift.
Oh, the sort of Arthur C. Clarke.
Yeah. So to go to low Earth orbit, take the skylift, and then use something like your nuclear saltwater rocket for the rest of the stuff.
Brilliant. We should have you on board day one. Like that sort of thinking. Yes. Anybody got any answers to the spaceships that are still on the screen? Come on, you must know some of these.
Got the Millennium Falcon.
Right.
Millennium Falcon, right? That's the
Space 1999.
Space 1999. Eagle.
2001 Space Odyssey.
Yeah.
And Blake 7, I can't remember the name of the ship.
Liberator.
Firefly.
Serenity, yeah. And this one, the one at the top middle.
No.
Nobody knows that? Okay, it's from what's it called? Is it The Day After Tomorrow? It's a science fiction movie. It has Brian Blessed in it, and they have the photon drive. So there you go.
Don't know that one.
Discovery 1,
Antares in Flash.
That's not 2001 actually. Millennium Falcon, Serenity, Space 1999 Eagle, and the Liberator from Blake.
Liberator. That was it, Blake.
Liberator.
There we go. Right, I'll stop sharing now. And
those take you back, don't they?
They do. Yeah.
Right.
Questions for?
I'm gonna leave.
Not a question, Dave. Just a quick comment. Julian, do you remember back in 1989 when the Galileo probe was launched, and there was demonstrations because it carried 50 pounds of plutonium, and the environmentalists were saying, well, you know, if this rocket explodes, it'll rain down in the area, and there was basically demonstrations. I'm not sure what happened after the rocket obviously launched and it went to Jupiter. I think it ended up crashing into Jupiter, didn't it? Pre-programmed to crash into Jupiter. But the actual launches after that, well, you know, I don't know whether they carried nuclear material afterwards. I'm just a bit in fear of all these proposed designs. It seems to be a heck of a lot of radioactive material seems to be the way forward.
Yeah, I have to say, I don't think anybody's looking at them seriously these days. But you know, in the 1960s, when the Cold War was at the height and people were pointing nuclear rockets at or nuclear warheads at each other, I guess these looked less dangerous at that point, given that they were probably thinking Armageddon was going to come any minute.
That's true. Yeah.
Why couldn't you use a conventional power station, but a smaller version for your nuclear reactor?
Yeah, that's basically all it is. You just
just a conventional nuclear reactor, like a sort of what you use a nuclear submarine, smaller than that, and then the propellant you have to use as well. You could use as steam, couldn't you?
yeah. You get the best bang from the buck from hydrogen because it's based on how heavy the molecule is, and the lighter the better.
Could you harvest your hydrogen from another planet somewhere?
Oh, maybe, yeah. So yeah, no, that's they have some clever stuff on that. Yeah.
Sorry, Julian. You were talking about launch sites, and I know this is going to be controversial, but penguins don't complain.
I think everybody can think of a place that you could launch nuclear rockets from.
And you use phosphine.
Phosphine,
yeah.
In terms of launching nuclear materials, of course, Perseverance is powered by
that's got an RTG on it. Yeah,
that left here, and virtually, well, anything that goes beyond sort of Mars area needs nuclear.
Yeah, all got RTGs on.
That's one of the big problems, I believe. They're running out of material for RTGs.
Yeah, I think they had to restart their production system.
I don't think they can because it's a nuclear weapons waste or something. It's banned by the nuclear weapons treaties.
Yeah, I think they've worked around it somehow. So they're not actually. There used to be loads and loads of it from nuclear weapons, so it sort of almost came for free. But they've had to, I think, come up with a new way of producing it. Just for these things, because New Horizons had it too, and
I did attend a lecture some while ago where I think someone working on a system for ESA using slightly different nuclear fuel, because ESA, of course, have always been totally against nuclear fuel, which is why everything's got big solar panels on.
Yeah,
but I think they've admitted if they go out to Jupiter or Saturn or something, they haven't really got any other option.
Yeah, there just isn't the amount of solar radiation that it's difficult to get any power out there.
Why don't you send a colony of people in a very slow rocket, and they just breed as people breed together, just get different generations of people. It might take thousands of years, but
So that's another idea, the generation ship, where you just launch the whole community, and there's quite a lot of science fiction books with that concept in.
The problem with that is you still need all your fuel and food and everything else and water and everything else to keep you going for 1,000 years or whatever.
Yeah.
You can't gather it in space.
No, I have to say it's not an easy idea.
You don't want to rely on airline food, do you? That's you
could grow your own food, couldn't you? You could have grown your own food, and the power up station would be just like a nuclear power reactor.
Yeah.
You throw methane as well.
Well, it wouldn't be methane, would you? You could produce methane if you wanted to.
God, April. Soylent Green.
Big greenhouse.
How do the SpaceX Raptor engines, going back to conventional engines, how do they compare to the previous conventional engines? Are they significantly better, or?
They're somewhere in between the Saturn V and Space Shuttle as far as ISP goes. They work on, is it methane? Is the latest ones. So yeah, they're not quite as good as hydrogen and oxygen, but a lot easier to manage, and obviously doing very well with them. Yeah. So yeah, I mean, rocketry is not all about ISP, and obviously thrust, and there's all sorts of other things calling it and managing the fuel and all that sort of stuff. So it's a lot more complicated than I made it, even with the maths.
Hydrogen's quite difficult. Older being so small as well, isn't it?
Yeah.
Any other questions for Julian?
No, thank you all for sticking with me despite the early maths.
Despite 2 sections of maths, most of us are still here.
Well done. You'll get gold stars.
Yeah, good stuff. Any other questions for Julian?
The Bepi Colombo rocket on its way to Mercury.
Yeah.
Uses the Ion rocket, doesn't it? I understand when I was talking with, I think, Professor Rothery, who was saying, to give you an idea of the force, which is very, very low, if you just blow on your hand very fast, that's about the equivalent of the ion rocket. So it's just the fact that it sort of builds up, I guess, the velocity in over continuous time.
Yeah, you kind of need months for it to kick in to do anything useful.
How they slow it down at the other end.
Oh, you just turn it around and use it the other way.
You also use Earth and Venus, of course, to actually lose some of the energy. So actually, we're just dumping the energy from the probe into the planets, in that case, to slow it down. Because the problem of getting to Mercury is, of course, you've got to lose energy. But getting to the Sun, it's not a question of gaining energy. It's a question of losing it and not falling into the Sun.
Losing it, yeah.
So the rocket is, the ion engine's firing backwards in the opposite direction to travel. Largely.
And that's why they've not sent many probes to Mercury historically.
Yeah, it's kind of harder than getting to Mars in some respects.
Yeah.
Right, very good.
Yeah. So, no other questions for Julian?
I've just got one, Dave.
Yes, go on, Pat.
Well, for a start, are dilithium crystals real? You know what they use on Star Trek? Are they real? And also, if you walk in space in one area, is it not affecting space everywhere else? Would it not have a knock-on effect? So you're sort of affecting the whole of space.
No, it's a very short-range effect. So space is quite difficult to warp, which is why they need all this exotic matter to do it. We found that with gravitational waves, for instance, they're very hard to shake space very much. So it dies away very quickly, the effect. And as far as I know, dilithium crystals are just a Star Trek thing. They're not real.
I was just wondering.
I was going to say, but I thought Star Trek was real.
Oh, no burst of puzzle.
Is that the same for flux capacitors as well?
No, they're real. No.
That's real.
Fusion.
I was just wondering about a passing interstellar asteroid and chucking a net round it and using that to accelerate your spaceship.
Yeah, you can do
need
that.
a bit of sort of absorption of the change in velocity, so a bit of rubber band will be needed.
Well, just like you can slingshot around planets, you can slingshot around the sun if you want to travel between solar systems. It doesn't do any good for traveling around the solar system, but in fact, Rendezvous with Rama, if anyone's read that, of C. Clarke, that's kind of the basis for that. They use solar slingshots to move on in the galaxy.
I was thinking more of Oumuamua or something similar coming past.
Yeah.
And just sort of capturing that and then whizzing out of the galaxy, out of the solar system.
Yeah, if you can catch up with it.
If you want to steer where you're going to, of course.
It's moving pretty quick, so you have to catch up with it first. All right.
Okay. So no more questions?
No more questions?
No?
Yeah.
Back to you, Dave.
No? Okay. Well, thanks so much, Julian. Absolutely fantastic. Frazzled the brain. So round of applause, folks. So brilliant. So understand a bit more about these crazy ideas that people have about these spaceships. So let's destroy the Earth trying to get up into space.
That's what it's all about. Yeah.
That's what it's all about. Yeah. Okay, excellent. So brilliant. Thanks so much, Julian, for giving the time tonight, and great talk again. Thanks everybody for coming in. There's still quite a few of us still left as well. So amazing. So again, thanks everybody coming in, making it the place it is. Meet up a couple of times a month. So you know what I'm going to say. Anybody got anything else to say before we go?
Thanks, Dave. Thanks, Julian.
Thanks, Julian. Brilliant.
Thanks very much.
Hey, Dave.
Thanks for another season.
Thanks, Dave, and thanks, Julian. Excellent talk.
Okay, right. Okay, right. Keep safe, keep well, and keep looking up.
Looking up.
See you, folks.
Bye.